All right, so on Desmos.com, we're going to choose this graphing calculator, and we want to graph what y equals secant of x looks like. So I'm going to go over here to the side, type in y equals secant of x, and there it is. Kind of an interesting looking graph. It's graphed here in red. Now, if I were to look at this, it looks like there's some vertical asymptotes in here, like some restraining lines in between all these different shapes. If I zoom out a little bit, I can see that those shapes do keep going up and down forever. How are we supposed to graph one of these secant curves? Well, I'm going to go over here to the graph settings, and on the x-axis, I'm going to have the step be pi divided by 2. Then I can get out of that. And you can see how that's significant in that we have a vertical axis or vertical asymptote at x equals pi over 2, at x equals 3 pi over 2, x equals negative pi over 2. So we're getting all these vertical axes or vertical asymptotes on very specific values. But again, how are we supposed to ever come up with this graph? I'm going to go over here to line 2. So just click over here on the left and type in y equals cosine of x. They're different colors so they stand out a little bit. And notice the relationship between our red secant curve, which is what we want to focus on, and this blue cosine curve. There definitely is a relationship there. Wherever this maximum was on the cosine curve is the minimum point for this portion of that secant curve. And then again, going on this blue cosine curve, the minimum for the cosine was the maximum for this branch of that secant curve. And then these vertical asymptotes for the red secant curve occur when the blue cosine curve had a y value of 0. And that's going to be our guiding principle as we look to graph these things. Let me X out of this second one. And we're going to alter the first one. Instead of y equals secant of x, we're going to put y equals 2 secant of x. So plug it in there. Did you notice what happened? So it's not in there, and now it is. If I go back down here, I'll go back to cosine. So y equals 2 cosine of x, and they have that same relationship again. If I can graph the cosine curve, that's going to be a big aid in trying to graph the secant curve. No matter how the cosine curve changes, it's going to impact the secant curve that we're trying to actually graph. So let me try this. I'm going to just click on this green part for a second to turn it off because I don't have to keep writing it over again. Go back to this first one and put in how about a -4? So again, it is -4. See what happened? Did you expect that to happen? From here to there? If I go down to the cosine one, do the same -4. So these two equations are mirroring each other. The only difference is the secant becomes a cosine. And if I turn on the second graph, there it is again. It's giving us the idea of what the secant curve is going to look like. So if you can graph this green one, use that to help you on the secant one, the red one that we're really looking for. It's all about reciprocals here. Let me go back to the very beginning, get rid of the -4, get rid of the 2 out front. Same thing down here and down here. Why are these asymptotes where they're at? Well, on this green cosine curve, the cosine of pi over 2 is 0. Since secant is the reciprocal of that, the reciprocal of 0 is undefined. That's what's leading to this vertical asymptote in there. So anywhere cosine was 0 is where the asymptote is going to be for the secant curve. Let's go back to the notes and put this in here. Question, what does y equal secant of x look like? We just saw an example of it on the Desmos. Let's go ahead and make our own copy on our own paper in our own handwriting. And to graph secant, we're going to graph the cosine first. The cosine is the graph that generates the secant curve. So I'm just going to graph a standard cosine curve, but I'm not going to make it dark. I'm going to actually dot it like it's like a shadow graph or like a ghost of a graph that we're going to use to get to the secant. So what does the cosine graph look like? Just the standard cosine curve. The period goes from x equals 0 to x equals 2 pi. The second period would go from 2 pi to 4 pi. I'll put the halfway point, the quarter point, the three-quarter points. The same thing in the second period. I'll get more details in a second. Maximum of 1, minimum of -1. That's because the amplitude is 1. It's not shifted up or down at all. And the cosine curve would have gone through this point, this point, this point, this one, and this one. This is like the outline of the first period of the cosine curve. I could do that again for the second period. And to continue graphing this cosine curve, instead of like full out graphing it, it's going to make it dotted. Because it's not really what we want, but it's going to serve as a guide as we actually graph the secant curve that we want. Next step, we need to get those asymptotes in there. Remember we had like these asymptotes that were these vertical restraining lines from left to right. To get those, we see anywhere that this parent function, it's not actually a parent function, this ghost function crosses this horizontal axis, we're going to get a vertical asymptote. So there's another one. There's another one. There's another one. Now within the region between these vertical asymptotes, I see that there is this point right here. I'm going to fill that one up. So if there was a minimum or maximum from the original graph, I'm going to use that point and then going away from the dotted lines or the dotted graph there, draw in my little horseshoe shape. So there's one part of our secant curve. I'll go to the next branch to the right, grab this point that is there, and again, go away from that shadow graph. At this point, this is one period. We need to have a down and an up to complete a period. So this is one period. I'm going to keep going. Here is another down. And between these three different waves, that's only a period and a half. We need to get two complete periods, which means I'm going to go back to my shadow graph again, extend it a little bit more, get another vertical asymptote. And now we have two complete periods. A period is an up and a down, and then another up and another down. So here is what the secant graph is going to look like. Secant can be kind of weird, but if we treat it like a cosine, which is just its reciprocal, use that as a guideline, then we can get our secant graph. Now, if I were going to put more detail on here, which is what I would recommend, which I'm going to require of you, then I need to get some more x values. So this x value is 2 pi, where the first period ended. That means this is pi, pi over 2, 3 pi over 2, 5 pi over 2. And this last one is going to end at 9 pi over 2. Just keep adding pi over 2 onto all these. And I have the x values for my first period, and then I have the x value for where that second period ends. This is the details I'd be looking for. What I want you to try is thinking about the same question. What does y equal cosecant of x look like? I'm going to pause for a moment and give you a chance to try to graph this one. If you want to use Desmos to give you a picture of it, think about what cosecant means, what its reciprocal is, and can you come up with what the drawing is going to look like? I'm also going to pause the video at this point. All right, so back on Desmos, this is the cosecant curve in red, and I have the cosine graph still in here. However, it doesn't track very well with that cosecant, and it's because it's not the reciprocal. So to get the reciprocal of cosecant, which is sine, I'm going to change that, and I can see how it tracks very well with that one also. It's hitting the same points. We have these vertical asymptotes. So this red is the graph that we want to draw. So let me go back to my notes. What does cosecant look like? Well, to get this graph, I want to graph sine. Sine has a period of 2 pi. The second period is going to end at 4 pi. I'll get my in-between values. And then the sine curve would start in the middle, go up to the middle and down, back to the middle, up, middle, down, back to the middle. Make this dotted because it's not really the graph that we want. And then anywhere that this sine curve hits this horizontal axis, in this case, it's a y value of 0, but occasionally we're going to be shifting these things up or down. So we want to see where does it cross this midline or this line of equilibrium. That gives us our vertical asymptotes. And then in each one of those regions, let me make that a little bit thicker here. We're going to draw these curves that hit the point that's in there and goes away from that shadow graph. Always going away. And this one would be 2 complete periods of the cosecant curve. I know it's 2 periods because I have an up and a down, and then another up and down. They look a lot alike each other, just like sine and cosine look a lot alike. They're just shifted to the side. They're going to have different vertical asymptotes. But the cosecant tracks along with sine because they're reciprocals. Secant tracks with cosine because those are reciprocals of each other. So 6 trig functions, sine and cosine, are the 2 most important. Secant and cosecant are the reciprocals of those. The other 2 trig functions are tangent and cotangent. Sine and cosine have their reciprocals, so we can use those to help us with the secant and cosecant. Tangent and cotangent are a little different. To get the tangent curve, we're actually going to go to a table of values. So this is the next page I have in the notes. We want to graph y equals the tangent of x by using the table to begin with. Now, tangent, recall, is sine over cosine, and we're going to try to use that to our advantage here. Knowing the unit circle, very helpful. So starting with 0, 0 radians. The sine of 0 is 0. The cosine of 0 is 1. 0 divided by 1 is 0. So there will be a point at 0, 0. Normally, I wouldn't include pi over 4 in. Like, I don't have pi over 6 or pi over 3 because we can get the graph without them. But pi over 4 is actually not that bad. It's actually going to be very helpful as we look to graph these things. At x equals pi over 4, the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is also root 2 over 2. And when you take something as ugly as it might be and divide it by itself, it comes out to 1. The tangent of pi over 4 is a nice, straightforward 1. Pi over 2, the tangent of pi over 2 is the sine over the cosine. So the sine of pi over 2, so we're talking about this angle going straight up and down. Sine of pi over 2 is 1, divided by the cosine of pi over 2. That's 0 because it's not side to side at all. 1 divided by 0 is undefined. Getting into the second quadrant. 3 pi over 4 is the angle that splits right down the middle. What is the tangent? Pause for a second. What is the tangent of 3 pi over 4? Answer would be a -1. The sine was positive root 2 over 2. The cosine was negative root 2 over 2. Divided, we get -1. Next, we're on to pi. So we're talking about this angle. The sine of pi is, or the tangent of pi is the sine of pi divided by the cosine of pi. That's back to 0 again. Five pi over 4 is the angle splitting right down the middle in that third quadrant. What would be the tangent of that angle? +1. We're back to being positive because there's a negative over negative. Next one, 3 pi over 2. So the sine of 3 pi over 2 would be -1. The cosine of 3 pi over 2 is 0. This is another undefined. Seven pi over 4 is now into the fourth quadrant. Hopefully you're picking up the pattern on this one. What's going to be the tangent of 7 pi over 4? It's going to be a -1. And lastly, the tangent of 2 pi. So we're talking about all the way back to this angle. 2 pi and 0, again, we call those coterminal. So since the tangent of 0 is 0, the tangent of 2 pi is also 0. The sine of 2 pi is 0. The cosine of 2 pi would have been 1. 0 divided by 1, yes, it's 0. So we have all of these values to help us graph. These values were chosen for a reason. I didn't pick a bunch of them. I picked quite a few, but I didn't pick the pi over 3s, the pi over 6s, because this is a quicker way to do it. If I had chosen the pi over 3s and the pi over 6s, we'd have like √3 over 3 or √3, a lot of decimals. These numbers in the y column are all very usable for us. Let's start putting these points on there.
Mr. Roth wanted me to give this to you.
Thank you. So begin with a point at 0, 0. Goes right through the origin. The tangent graph goes right through the origin. And then there's a point at pi over 4, comma 1. So this is pi over 4. The next x value is pi over 2. It's undefined. And like we had for the secant and cosecant curve, this undefined is going to be another vertical asymptote. Three pi over 4 is at -1. Pi is at 0. 5 pi over 4 is at +1. And 3 pi over 2 is undefined. Go a little bit further to the right. 7 pi over 4 is back at -1. 2 pi is back at 0. These points are supposed to give us a clue about what this graph is going to look like. Now, if you're not sure, we have some technology. Why don't you go back to Desmos and enter in y equals tangent of x, and let's see if we can piece together what this graph is supposed to do. We have the most important things about this one, and this is eventually this is going to be enough for us. Like if we have these points, great, I can graph this one. I know exactly what it's going to do. But give yourself a chance. Look on Desmos. What is the general shape of this tangent curve? So I'm going to hide this one. Go back to x, and we have all these little swooshes going through there. All these little swooshes going side to side. They're not jagged. They're very smooth curves. They're going through that point right on the horizontal axis, and you can see where those vertical asymptotes would line up. So on our graph, we're going to say this looks like this. Like we've done for the other ones, we're going to graph 2 complete periods. Unfortunately, we only have 1 period so far. So we have to go further to the right. Another dash will give us this point. Another dash to the right will give us this other vertical asymptote. And now we have 2 complete periods. We'll talk about how much detail we're going to put in these graphs as far as what x values we want for the asymptotes and for the points that are out there. But this is what the tangent graph is going to look like. Sine and cosine, I know some graphs you looked at last year. They have those nice smooth curves going up and down. They're waves. This is what tangent's going to look like. These little swooshes going from left to right. From left to right, it does have a positive graph or positive slope. It's going up from left to right always. Which leads us to cotangent. Let's go back to Desmos again. And I'm going to keep y equals tangent of x on there, but click and now do y equals cotangent of x. gives kind of a neat pattern. If I get rid of the tangent of x, here's what cotangent looks like. So again, red is the tangent. Red is doing this. The tangent goes through 0, 0. Tangent goes through the origin. From left to right, it is increasing. The slope is positive. Whereas for the cotangent, it does not go through the origin. Actually, x equals 0 is going to be one of our vertical asymptotes. And from left to right, cotangent is going down. The slope is negative. So they're not the same graph. They both have like little swooshes in, and they have very similar shapes. The first one, tangent, out of SOHCAHTOA, so tangent is a bit more important. The tangent gets to go through the origin, and the tangent is the positive one. Whereas cotangent uses x equals 0 as the vertical asymptote, and it does not get to go through the origin. It is the negative. It goes down from left to right. The slope is decreasing. So on my OneNote, rather than filling in all these values, which I could do, I'm just going to take what I just learned and try to graph this thing. So x equals 0. There was a vertical asymptote. That's because the cotangent of 0 would have been undefined. And unlike sine or cosine, as well as secant and cosecant, the period for tangent and cotangent is smaller. Go back to Desmos one more time. The period, like for one of these little swooshes, each of these swooshes is a period. The period for this cotangent goes from x equals 0 to x equals pi. So x equals pi, vertical asymptote. X equals 2 pi, next vertical asymptote. To figure out what the graph looks like, I'm going to go right in between these vertical asymptotes. Halfway between 0 and pi would be pi over 2. And what do I know about a cotangent curve? It's the negative one. It's going down. Halfway between pi and 2 pi would be 3 pi over 2. And cotangent is negative. It goes down. There's a cotangent curve. So 6 total graphs, sine and cosine. Those were the originals. Those are the ones we did all the transformations on. But now we have secant and cosecant, as well as tangent and cotangent.
Can you go back and compare, like,
Yeah, so they're intersecting right at this point. It's kind of a weird point, negative 11 pi over 4 comma 1. That's where the tangent and cotangent would be equal to each other. You can see that again. There's like going to be a negative one down here as well. Again, it's the pi over 4s. The tangents and cotangents love the pi over 4s because they're either getting positive 1 or negative 1. Again, it kind of creates a cool looking shape here. My big takeaway for you is for the tangent, it goes through the origin. And even like the word tangent, like this almost looks like an x and y axis, right? It's the letter T, but it looks like x and y axis. Tangent gets to go right through that origin. The other thing that the T in tangent looks like is kind of like a positive sign because coincidentally, it has a positive slope. It's increasing from left to right. So the difference between those two, tangent goes through the origin and tangent has a positive slope. Whereas cotangent has x equals 0. It does not get to go through the origin. It has x equals 0 as a vertical. Cotangent going down. Let's go back here. So those are our intros to those. Let's get into actual 4.6. I'm going to skip this stuff at the top for right now and go down to this first example. Our goal here is to graph y equals secant of pi x plus 1. Because it's secant, it might seem like, oh my gosh, this is going to be terrible. It's a weird one. We're going to treat it as if it were the cosine. The reciprocal of secant is cosine. Let's pretend that this is a cosine for right now and go through the entire process. What is the amplitude of this one? 1. What is the period of this one? 2. 2 pi divided by pi, the period is 2. It doesn't shift left or right at all. There's nothing like added or subtracted inside of the secant. We do have this plus 1, which means the whole thing is going up by 1. And that's the only variation from the original. So, as far as the graph of the cosine goes, I would say, okay, shift it up by 1. Since the amplitude is 1, the high point is 2, the low point is 0. Make your line of equilibrium, shift it up by 1. There's the y-axis setup, same thing we were doing before. The period is 2, so I'll say, all right, this distance is 2. So half of that is 1, 1/2, 3/2. The second period is going to end at 4. Put all those little hash marks on there. Again, I'm pretending this is a cosine right now. I'm getting everything set up as if it was a cosine curve. So continuing with that, because it's cosine, it would normally start at its maximum, middle, to the minimum, to the middle, to the maximum, to the middle, minimum, to the middle, to the maximum. Like this would be what the cosine would look like. Make it a dotted graph. And treating it just like cosine for right now. We need the vertical asymptotes. The vertical asymptotes are where this shadow graph intersects this new midline, this new line of equilibrium. So at x equals 1/2, we have one. X equals 3/2. I don't have this one labeled right now. There's another one. And then draw in your horseshoes. How many periods is that so far that I have up on the screen? How many periods is that? 1.5. 1 complete period because it has a down and an up. Half a period because it has a down, and now I need an up. And you can decide. You can go back over here to the left and extend this to the left and get another one over here. Or you could extend it to the right and find one over there. There is a secant graph. I want you to try this one.